Alright, good. So, we've made some progress with single qubits. So, now let's try to generalize to multiple qubits as usual. So, one thing that is sort of becomes really important when we talk about multiple qubits is the notion of partial measurement. So, what happens in partial measurement? Basically, if I have a bunch of qubits, it's possible for me to only measure one of them, right? So, let us take the toy example of just 2 qubits, okay, and let us say that I only measure one of the 2. Can you tell me what should be the probability of the first qubit being 0? That is exactly right. So, what he said is, it should basically be alpha 00 squared plus alpha 01 squared, and that is exactly right, because these are, this is the probability that it will collapse into a state which has the first qubit as 0. Right. So, let us write this down. So, it is going to be alpha 00 squared plus alpha 01 squared. Okay. And now what remains after I do this? So, now basically in this particular example, right, I know that since I got 0 as the first qubit, I know that these terms are no longer relevant, isn't it? I performed a partial measurement, I got the first, this is all very intuitive, right. So, I have 2 qubits, I performed a partial measurement, right, I got that the first one is 0. So, obviously all those parts of the combination which involve the first qubit being 1, these are no longer valid, right. So, now this 1 0 1 1, this goes away, okay. And what remains? Well, basically I just drop the invalid terms and renormalize, okay. So, just drop the terms where the first qubit is 1 and renormal. Renormalize, and you'll end up with this state. It's really very easy to see. So, I mean, the fact that I dropped the terms where the first qubit is 1, that's obvious, and the renormalization is also obvious. Okay, so I've just renormalized so that the sums of squares will be 1. Any questions? Okay, good. So, we are ready to get into the sci-fi stuff. So, entanglement, okay. So, this is what most people who have not studied this are most curious about this this particular term, entanglement, okay. So, this idea of entanglement has a it has a very rich history as well. So, because it seems that Einstein did not believe that this can be possible, and he called it spooky action at a distance. We'll see why he called it that, but actually, well, I mean, it is possible. So, that has been established. It was established back then itself. So, let's see what it is, okay, first of all. So, what does entanglement mean? Okay, I already told you in a previous class that this state is an entangled state. So, this is an example of an entangled state. It is perhaps the most famous example, 1 over root 2 0 0 plus 1 1. What does it mean? Basically, what it means, I mean, just with the little bit of language we have developed so far, we can already understand this very rigorously. What it means is simply this, if I perform a partial measurement here, let us say that I measure the first qubit. So, now if the first qubit comes as 0, first of all, what is the probability of the first qubit being 0?
1 by 2.
It's half, right? And I mean, obviously also of being 1 is half, right? Okay, so I measure it, with yeah, so with probability 0, let me write here, right. So with, actually let me not go there yet. So if I measure the first qubit with probability half, I get 0. This is if I measure first qubit. With probability half I get 0, with probability half I get 1. Now what happens to the other qubit? What happens is very easy to see. Basically, you know, I am now either in this state or in this state, right. I cannot be in both at the same time because I have done the measurement. And if I am in the first state, then I know when I observe that the first qubit is 0, I know that the second one is also 0, though I never measured it. And what was very sort of surprising at that time when this idea was first discovered is that in the beginning it seemed to violate the law of the speed of light. So basically what can happen now is, let us say, you know, we prepare this EPR state. So first of all, you should ask, how do I prepare this state? So we will answer that in this class itself, but for now we will postpone it. So you know, just using the few gates that we have seen, we can show that this state can be prepared. Now if I prepare this EPR state, right, so now I have 2 qubits with me. Let us say that, you know, I keep one with me, I give one to Anuja, right, she catches a flight and she goes off to, I don't know, where do you want to go? Okay, to the Maldives or something, she goes there. Okay, and I perform a measurement here, and this determines her qubit. Her qubit, even though, you know, she is far away and we have no way of talking to each other, or we have not talked to each other. So this, you know, was considered very surprising, because it is what Einstein called the spooky action at a distance. So because, you know, information should be rate limited by the speed of light. The speed of light is the fastest, right. So in some sense, you know, it is like a communication that has occurred without obeying the law of the speed of light. It appears like that, but it turns out that it is not a violation, because in order to convey the information to her that, you know, I measured the qubit and it turned out to be 0, I still need to pick up a phone or whatever and tell her, and this will be subject to those laws. So anyway, I do not want to get into this much more, not that I even know much more about what all were the worries and the interpretations, but this is what entanglement means. Okay, so a little bit more formally, we are going to say that a system of 2 qubits is entangled if it cannot be written as the tensor product of 2 qubits. So now look, this is a formal definition, right. So far what we saw was an example. We saw an example of the EPR state, and we discussed how this idea of entanglement is represented here, right, that basically I measure one qubit, the other one is determined. The formal definition is that you know, this state should not be writable as the tensor product of 2 qubits, and now again I want to ask you why. So let me look at, I mean, not why the definition, but why does this state satisfy this definition. So look at this state. I claim that you cannot write it as the tensor product of 2 qubits. Why is that? Okay, good. So what he is suggesting is that, you know, well, I could try to take 2 states and then write down the coefficients and compare. So actually that would work. There is a cleaner way of looking at it also, but let us first try the idea that was suggested in the class. Okay, so now let us say that, you know, I have some psi 1 and some psi 2, and let us say that this gives me whatever alpha 1, alpha 2, alpha 1 beta 2, right, and then beta 1 alpha 2 and beta 1 beta 2. Okay. So, I hope that this at least is clear, right. So, this is just alpha 1 beta 1 tensor alpha 2 beta 2. Okay. Now, what is this equal to? Let us look at this EPR state. So, what is 0 0? So, remember our basis for 2 qubits, right. So, this is basically going to be what? 1 0 0 1, isn't it? So, I got this. Now, this already sort of gives me a contradiction, right. So, let me for the sake of completeness write here that we are assuming otherwise and trying to make it work. Okay, because see, alpha 1 alpha 2 being non-zero means that none of them is 0, right. Similarly, beta 1 beta 2, none of them can be 0, right, but then that gives me a contradiction because the middle coefficients are 0. So, I arrive at a contradiction. So, sure. So, you know, when in doubt you can always open it out and play with it, and oftentimes it works out. But a cleaner way of looking at this is considering the rank. So, you know, if I organize this tensor product, if I organize it as a matrix, okay, if I take the tensor of 2 vectors, what is going to be the rank of the resultant matrix? So, I claim it can only be 1, whereas if I write the EPR state in terms of a matrix, right. So, if I write, so let me say I so this is 1 0 0 1, right. So, this is just this, right. So, this is written in terms of a matrix. Okay. This is a tensor product matrix, this has rank 2. So, I cannot write it as the tensor product of 2 other vectors. So, this is just this thing about rank which I said is just a property of tensor products, okay, that the rank of this tensor product will be the product of the ranks, right, and the product of the ranks will just be 1, whereas here we see that the rank is 2. Okay, so, this is the definition. So, a system of 2 qubits is entangled when it cannot be written as the tensor product of 2 qubits. Okay, this is our definition. Alright, so this we already talked about. Nevertheless, I will, for the sake of completeness, write it here. With probability half, I get 0, right, if I measure the first qubit. With probability half, I get 1. And when I measure the second qubit, I get the same answer as when I measured the first qubit. Okay, so even though Anuja has her second qubit and she is far away, I know when I measure mine, I know what she will get when she measures hers. Okay. And this was the sort of the famous spooky action at a distance, that you know, measuring the first tells you something about the second, no matter how far apart the qubits are.